So for the time being, we're going to leave vectors behind for a little while. Now we're going to actually look at more of the bulk of Calc 3, starting with this chapter and the next. But before we do that, we're going to talk about...
So are these chapters harder? More difficult?
Much more difficult, yes. Alright, so we already know that the notation f of x represents a function in terms of x. Sometimes we also call this y. Now, in 3 dimensions, or in 3 space, instead of using y as the dependent, we use z as the dependent. And now that will be defined as a function in terms of x and y. So this is the common notation that you're going to see. So this is a function in terms of x and y. This is dependent, and then these are your independent variables. Bless you. Now you've already dealt with some multivariable functions. You just didn't really think of it that way. One example would be like the area of a triangle, half times base times height. This could be called a function of what? B and H. Okay, so you've already seen these before. This idea can also be extended into more dimensions. So sometimes you'll also see maybe w equals f of x, y, z, etc. Okay. So that's just some notational issues. Now typically, and now this is why mathematicians like our 3D axis the way we have it. We like the dependent variable being this z-axis. For one, usually the graphs are easier to sketch. Okay, so this is the dependent, and now your domain will be determined by your xy values. So the domain, I guess you can say it's the restrictions on x and y for f of x, y. So for example, if we have a function f of x, y equals natural log of x, y, what is the domain? One can or can't?
Yeah, one can't be negative while the other one's positive. You know what I'm saying?
I do, actually.
Yeah.
So xy has to be greater than 0.
But you don't specify for x.
But no, I mean, that I like the way you said that. They both have to be positive. What quadrant is that?
The first.
Or they both have to be negative. So that's quadrant 3. So you can write the domain a couple of ways.
You can write it like that.
You could say all x comma y's that are in quadrant 1 and 3. You could also say all ordered pairs x comma y such that the product xy is greater than 0. But it is nice to have a visual of what the xy plane looks like, because now when you translate this up here, if we're talking about quadrants 1 and 3, that means that you would expect that the graph would only exist, above or below these planes or those parts of the plane. Does that make sense? Okay, because once you have an x and a y value that determines your z, you're either going to go up or going to go down. So you're not going to see any part of the graph below or above these quadrants here. Okay. Let's try one more. Let's say f of x, y, z equals x over the square root of 9 minus x squared minus y squared minus z squared. How do we find the domain here? Yeah.
We can write like x squared plus y squared plus z squared is less than 9.
Okay. Oops. Has to be less than 9. Okay. And how'd you get that?
Because the domain restriction is the square root in the bottom, and we're subtracting x squared, y squared, and z squared, so those have to be less. We have to subtract less than 9.
Bless you. Okay. Yeah, that works. So, and we don't want to be equal to 9 because then you have 0 in the denominator. Okay. What shape is this, by the way?
Sphere.
It's just a sphere centered at the origin, right? Radius 3. So yeah, essentially as long as we're within the sphere but not on, right, this would be a valid function. Does that make sense?
Can we write like
You could say this, x, y, z, such that, whoops, can't spell today, such that this is true. You could also write it's all x, y, z inside a sphere of radius equal to 3 centered at the origin. Okay? And just for good measure, if I asked you to find, let's use the same example, f of 2, 1, 1, you guys know what to do with that, right? Just plug it in, yes? So what would we get?
x over root 3. Or, I'm sorry, 2 over root 3.
2 over root 3, good. All right. So your ideas from Calc 1 with single variable pretty much stays the same. Domain is a little different because now you're looking at more than one variable at a time, but it's no big deal. Okay, graphs. We know that y equals f of x translates to, something like this. Now we're going to look at z equals f of x, y. So instead of being a two-dimensional function, it is a three-dimensional surface. We've already talked about surfaces before. Usually we had like z equals x squared plus y squared, right? It's the same thing except now we're calling them f of x, y. So maybe something like so this could be z equals f of x, y. What's that? Okie dokie. So as far as graphing, I don't really want to spend too much time talking about it because you already know how to do it, but maybe we'll do one quick example. How do you graph f of x, y equals square root of 4 minus x squared minus y squared? What's that, Carl? Yes. Want to tell me how to draw it?
It looks as if you. It looks
squiggle.
Because it's a cylinder. Because there's no.
Let's think of it first like this. This is the same, right? This is not one of the usual formats, so why don't we square both sides just to see what happens.
Isn't that z-squared?
Isn't what z squared? Yes, yes it is. Okay. So this is essentially, if you move stuff around, what? Sphere, center at the origin, radius 2. However, this square root restricts z because it's always going to be greater or equal to 0, right? So the actual graph is just the top hemisphere of the sphere. So something like that, I don't know. This isn't hard, right? You guys were all worried. We're almost done with it, believe it or not. Any questions so far? Okay. So, yes, you're going to have to remember how to graph those equations from Chapter 11. Yes, you're going to have to be able to modify them, move them, translate them, and so on. But,
I know, seriously.
well, looks like you'll be using that a little bit more than just. So the last thing that we need to talk about are level curves and contour plots. So let's suppose we have some surface let's say this is z equals f of x, y.
Someone's failed clay project.
I'm trying to make this more interesting than just a little elliptical paraboloid. Here's the definition for a level curve. A level curve is the curve formed by slicing a surface with a plane z equals k projected, don't worry, it's not a vector projection, onto the xy plane. So, if I were to take, for instance, yeah, it's a cross section. If I were to take a plane, z equals k, and just slice straight through the surface, maybe we get something that looks like this. So maybe that's what we're looking at when we slice it. So then all we would do is literally map this straight onto the xy plane, and now this is a level curve. Yep, that's exactly right. Any questions on what a level curve is? Okay. Then, let's try this example. Let's say we have f of xy equals x squared plus y squared. And we want to sketch level curves corresponding to z equals, let's say, 1, 4, 9, and 16. I'll see you guys. So, what is the graph of this? It's a paraboloid. So this is f of xy. Now, and I think you understand, if you were to slice horizontally, right, through the surface, what curves are you going to get? Circles. Okay. Now, the level curves are just going to be x squared plus y squared equals 1, x squared plus y squared equals 4, and so on, and x squared plus y squared equals 16. So, if you graph them, you're just going to get circles with radius 1, 2, 3, that was pretty bad, sorry, and 4. Now, if we only look at the xy plane, so let's do the same example and just talk about the xy plane. And I graph all these level curves on the xy plane. Then we have something that looks like this. And since this is a set of level curves, now this is just a set of some of them, but the set of all level curves is called a contour plot.
Wouldn't there be like an infinite number of curves?
Yes, but we can't draw them. So this is just a snippet of the contour plot, if you will. Okay, and each one of these curves corresponds to different z values, right? This smaller circle corresponds to z equals what? The next one?
2.
Are you sure?
4.
9. Okay. Have you guys ever looked at maps, or like if you go to parks or like hiking and you look at all these little hills and mountains and stuff like that, and they have all these little curves? I mean, not like you'd never go hiking somewhere that was like this.
Isn't it like the altitude?
But yeah, essentially you follow the line, right, and it tells you how high up or what the altitude is, right? This is exactly what this is. If you're on the circle, what's the height? 1. If you're traveling outward, what's going to happen to your height?
It's higher.
It's going to increase, right? This is what a contour plot does. This is how it's created. You just take slices of all the planes z equal to k, you project them all onto the xy plane, and you get some curves that have corresponding heights. Okay?
You would do it there in maths.
It would be. Does this make sense? Okay. This is actually very, very applicable. Okay. You know what? I guess we can just finish with one more thing, and then we'll call it a day. Now, there is a thing, not just level curves, but called level surfaces. So if we have f of xy, the graphs, we get a surface, okay, And then if we project onto the xy plane, we get level curves. If we have a 3-variable function, f of x, y, z, this is now a 4D graph, which we're not going to draw. However, the concept still stays the same, that if you were to set, let's say, w equals f of x, y, z, and we say find level, it wouldn't be level curves anymore, they'd be level surfaces corresponding to, let's say, w equals 1 and w equals 2. Let's say the graph is f of x, y, z equals x squared plus y squared plus c squared. Okay, I don't really have a way of graphing this, but we could find the projections onto 3 dimensions from this. And you would do that by plugging in values here. So what would the level surfaces be? This is a sphere. Yep.
So what would this 4D graph look like?
You won't be able to imagine.
Well, this is as good as we can do right now. No, it's totally real. We'll even be integrating functions that are 3-variable functions.
This isn't mine. Are you a troll? I just told him.
Is the radius 2?
You guys probably already know how this stuff's going to work. When you integrated f of x, what did that represent?
Rate of change of
When you integrated f of x, yeah.
Is the radius root 2 or 2?
Yeah.
the area
Is it
under
root
the
two?
curve.
It's root 2, yeah. Thanks, Charlie. When you integrate f of x, what do you get? Area under the curve f of x. When you integrate f of x, y, what do you get?
Area
You get a volume under a surface, which we'll talk about next unit. If you integrate f of x, y, z,
What is this?
You get the
it's
sum.
called a hypervolume.
What?
What do you call it?
Hypervolume.
It's called a hypervolume.
What exactly is that?